Hello friends, I'm Sumit. This is my YouTube channel Massive. In this video, I'm going to decode one scene which was deleted from The Beautiful Mind, a movie which has been very close to our hearts. I watched it for the first time in my graduation when I was pursuing my graduation, and few years ago I have come across one scene on YouTube channel, and few days ago again I have come across that scene, the deleted scene of Beautiful Mind. So this time I decided that I'm going to try at least to decode that scene, and I can share the link of that deleted scene in the description. You can watch that uh, while pausing this video, and can resume this video after watching that short clip. So in that deleted scene, okay, let me talk about one more scene. So this was part of the movie. This scene was part of the movie. As we all know that in that movie, the character who was playing the role of John Nash, he thought himself probably the best mathematician. Of course, he was pursuing his PhD in Princeton University, a university which is probably one of the best universities in the world for multiple courses, for multiple fields, multiple subjects. So he thought that he was the best, and he was asked by his batchmate to play some board game. And in that board game, the great John Nash was defeated by his batchmate, his opponent. And since he was so adamant, he said that the game is flawed. Let me quote him. He said the game is flawed. I had the first move, and he got fumbled, disappeared from there. So, so he was damn sure about his excellence that he said that since he had the first move, how he could be defeated. So he told his batchmate that the game is flawed. And then in that deleted scene, you know, he suddenly barged into one room, telling his batchmates, "Well, see, I've come up with some, you know, another board game, a game of Hex, where the person who has the first move can have one winning strategy. Can have. It depends on how good, how excellent that person is. But yes, if you have the first move in this game, you will have the winning strategy. If you're smart, you cannot be defeated. If you win, you deserve to win." That's what he said in that scene. And he also, said in a very subtle way, he basically gave us some clue that black is land and white is sea, and suddenly disappeared. So he was basically referring to the fixed point theorem. So in this video, I'm going to I'm going to bring the link between game of Hex and fixed point theorem. I'm going to tell you how this game is played in case you get bored while playing a chess or tic-tac-toe, uh, where the uh, game like this where we have to either put cross or zero, and but in this game, in this board game, it can result in draw, and even chess game can result in a draw, but game of Hex, it cannot result in a draw. And this can also be proved using fixed point theorem. So today I'm going to tell you that how this game is played, and how we can use the fixed point theorem in proving that this game can never result in a draw. One has to, if two players are playing this match, then one has to win the contest, other will be losing the match. Okay, now let me start. So this is the fixed point theorem. I'm going to discuss it in few minutes to come. So first let me tell you, and why it is called game of X, because you see each box is hexagon, each cell is hexagon. It has 1 2 3 4 5 6, it has 6 sides, so it is hexagon. That's why it is called game of X. Now, so there will be two players, okay. One player would be trying to, so one will be placing their some kind of, they will be placing some key, or you can say they will be marking or filling these cells one by one, and each one will be trying to cross, either to basically to connect the leftmost cell with the rightmost cell continuously, or it depending on who gets to play from which side. So if suppose player A is playing from the left side, then he will be trying that the uh, he will be trying to connect the cells from the left most side to the right most side continuously without a break. And in the same way, if player 2 is playing from say this side, then he will be trying to connect from right from the bottom to the top continuously. So there has to be some path, continuous path. But as I said, that this game cannot result in a draw. So first let's just play this game. Okay. Suppose one player is playing from the one player starting is one player attempts to uh, connect from the left to the right, and suppose he is filling his cells with yellow color. So, and suppose another player is going to connect from bottom to the top, and he will be filling his cells say through red color. Okay. So suppose he starts first. So say he fills this. Now the second player comes and he says he's going to fill say this. Now he fills this. Now I'm just trying to be random. Okay. Then I have to fill this, right? Otherwise he will win, right? So I do this, then do this, then well, if I fill this, then this player would win, right? But okay, let's continue this. Suppose if I fill so 1 2 3 4 5 1 2 3 4. So red has the next move, right? So let's do this. Now I have to do this. Now I have to do this. Now okay. So what I'm going to do? Well, if I fill this, then yellow is going to win because it's a continuous path. If I'm going to fill this, then only one is left, and in that case, this player is going to, because this is the continuous path. Okay, so you can see that it cannot result in a draw. Okay, one has to win the match, and intuitively I can also, okay, just hang on. Intuitively also I can prove. Just try to think from your end how it cannot result in a draw. Okay, suppose suppose there is one river flowing in this direction, and the water is flowing in this direction. Okay. Now the water is going to flow from point A to point B. The water will reach there unless there is a dam built right in the middle of the river. If there will be some small pores there, on the dam wall, then still water will find its way and reach its point. So either it will reach there, or if the water is not able to flow, not able to cross past this point, then it means that there is a dam which has been built, which is blocking the flow of the river. So in a way, dam has been built without any pores. So either this point is connecting this point, or the water is able to flow from point A to point B. So I am pretty sure that you are able to understand what I am trying to convey here. So now let me talk about the fixed point theorem. So you know how the game of X is played, and you know that it cannot result in a tie. Okay, it cannot result in a draw. So you see the function is, if the function is continuous and if it is mapping from this set to the same set, so function is continuous. If the function is continuous and if it is mapping to itself, then there will exist one point, there will exist at least one point x belonging to the domain AB, which is a closed set, such that f of x is equal to x. So I've okay, you will be able to understand it through uh, this graph. So I have drawn one 45-degree line. Why? Because on 45-degree line, x will be equal to y, which is fx. So x will be equal to fx on each point of 45-degree line. Whereas function, basically this is the graph for fx. Okay, so at value of a, we are getting this much value of fx. Okay, at this value of fx, at this value of x, we are getting this much fx. At this value of x, we are getting this much fx. So function could have taken any different shape. Okay, this curve would have taken any different shape, but it is not difficult to understand that this function will cross this 45-degree line at least once, unless it is discontinuous. And we have already assumed that if the function is continuous, then the theorem will hold true. Okay, so suppose if the function would have been like this, say it decreased. So it's basically cutting here and here. So there are two fixed points. Had it been like this, it would have cut the 45-degree line at this point, right? Or it would have been like this also. So it depends what kind of mapping we have chosen, right? So function could have taken any shape, but yes, at least once it will cut this 45-degree line. Now let me tell you, what if the function would have been discontinuous? Then I'll try to tell you that in that case, we may not have witnessed even single fixed point. So 1 second, just hold on. Um, so suppose if the function would have looked like this, and right at this point, say x dash, we see sudden drop in the fx, say this and this. So you can see that right at the point of x dash, we have this as the f of x dash, and there is a discontinuity. And in that case, the function is, the value of fx is not touching 45-degree line even at single point of x along the x-axis. So in that case, there won't be any fixed point. So yes, so basically this theorem would hold waters only if the function is continuous. Okay. All right. So all right. Okay. All right. So far, you are. I hope you are able to understand the intuitive idea behind the fixed point theorem. Now, let me make it. Let me make it. Let me make it clear to you in a much better way. So, suppose this is circle A. Okay, and this is circle B. Okay, and in this set you have multiple points. Okay, like it's filled with many points. Okay, now you see, if I tell you that each point is mapped identically and both are the same sets. Okay, I mean, I mean, the radius and the circumference, diameter, everything will be same in both the circle. So in that case, if I tell you that each point in circle A, consider it as your domain, okay, and consider it as your output codomain. So in that case, this, if every point is mapped identically in circle B, then you tell me which points or which point would be the fixed point in the circle. Every point in circle A will be a fixed point, right? If I tell you that each point has been rotated 90 degrees, so suppose if there was a point here, then this point will be mapped here. If there was a point here, then because of that mapping, that point will be mapped here in circle B. If there was a point here, then due to 90-degree rotation mapping, that point will be mapped here. So in that case, if you know we have there will be so many points which will be mapped accordingly, then which point will be the fixed point? In that case, only the point which is at the center will be the fixed point, because in that case it will not move, right? So that is the only fixed point. Similarly, if I'll tell you another special case, so suppose if the mapping is such that every point is mapped to a single point, say here, that's it. So everything, so it's basically many to one function. Each value of x in this circle is mapped to a single point. So basically it's like so function would look like this, horizontal line, because f of x is not going to change no matter what the values of x are. Okay, in that case, what would be the fixed point? You tell me. The fixed point would be point which is corresponding to this point in the circle. So if this, suppose if this has been, everything has been mapped to this, or suppose everything has been mapped to this, then in this circle this will be the fixed point, because otherwise all other points have been shifted differently, but this point is mapped exactly where it was here. I hope I'm able to clear. Now let me tell you one more case. To talk about the problem related to discontinuity. Suppose if everything is mapped to this, but the center is mapped here. What I'm telling you, that every point in this circle is mapped to center, whereas its center point, except this center point, everything in this, see, I repeat, every point in the circle is mapped to the center point of circle B, except the center point of circle A. So where it is mapped? Suppose it is mapped here. In that case, there is no fixed point in circle A. And why? Because see, when we say that function is continuous or mapping is continuous, it means that the value of fx should change very gradually. It should not take like too much. You should not witness too much change. Okay, it should be continuous. F of x should be continuous, no matter whether it is increasing or decreasing or stay constant. It should be constant. But in this case, everything is mapping to this, and suddenly, when we reach, like if we suppose if we are moving from these points to center, then it stays here only. Function is still continuous. The moment it reaches the center point, the f of x changes from this point to this point. In that case, there is a discontinuity, and you can see that no point in the circle is there's no such point in the circle which is a fixed point, because everything is mapped to this. So x is not equal to fx in that case, and ideally this should have been equal to this, but mapping is such that this is also not equal to this. So f of x is not going to change, and only this point could have been fixed point, but that point has been mapped very differently, and that point has been mapped to this. So there is no such fixed point. Why? Because we have a discontinuity. I couldn't make it clear in much better way. So I think I tried my best. Now let's move forward. And try to relate the game of x with the fixed point theorem. All right. Now so see. Okay. So now since we have a good idea about fixed point theorem, now let me proceed how we can use fixed point theorem to prove that game of x cannot result in a draw. So we have to have some mapping, right? We have to have that function which is continuous, and so that function will be using the, so basically consider this So basically these points, which I'm going to draw randomly, and those points will be mapped within this set in a different way. Okay, they are going to be transformed. That's what the mapping means actually. So all the hexagonal cells which I'm going to draw randomly right now, those hexagonal cells are going to be transformed into some different cells within this hexagon board, the game of X board. Then we are going to link this fixed point theorem, because we are going to apply that mapping. That transformation will happen because of this function only, and this function has to be continuous. All right. So, but since it will be, so basically we have hexagonal cells, right? So it will be easier if we consider each hexagonal cell. We symbolize each hexagonal cell with some point. Okay. So suppose this hexagonal cell is symbolized by this point. This hexagonal cell is symbolized by this point. This hexagonal is, suppose this point, represents this hexagonal cell. Similarly, this point, this point, this point, this point. Okay. So these four hexagonal cells, it is equivalent to say that this hexagonal is linked to this, or this point. It will be easier, like for our own convenience, we are just doing this. This point is connected with this. It means, since this is the point, this center point of this hexagonal cell, and this point is connected to this point, then this hexagonal cell is also connected to this point, or this hexagonal cell, right? So consider the center points of each hexagonal cell as the hexagonal cell only, right? So it's not hard to visualize this way. Okay, so each point really sorry, I created a mess here. So each point, you can see, each point in the hexagonal cell is connected to the other points of hexagonal cells, right? All right. Now, suppose this is the hexagonal cell, and suppose applying some function. Okay, suppose this function is mapped to this hexagonal cell. In that case, we can say that the mapping is giving this vector. It's basically moving upward. And suppose if the function would have been like this, that this hexagonal cell would have been mapped to this hexagonal cell, or transformed to this hexagonal cell. In that case, the mapping would have seen, say, suppose horizontal vector. So it is not difficult to understand that either we would have horizontal movement or vertical movement. Vertical movement would be defined by this. Horizontal movement would be defined by this vector. So this is the vertical vector and this is the horizontal vector. So far so good? Okay. Okay, so to prove that one will always win this match, I'll be using fixed point theorem. And for like to use fixed point theorem, I must have a well-defined function. Okay, which should be continuous and which should map to itself, because I'll be using fixed point theorem. So, but before I define a function, let me randomly fill these cells one after the other using different colors, and you will get to know why I'm going to do this, because I'm going to use that information when I'll be using that function. Okay, don't worry, have some patience and you will get to know what I'm doing right now. So since there are 16 cells and each cell would be filled by each player would be filling their cells using different colors one after the other. So 8 cells would be filled by, say, player 1 using say yellow color chalk, and other 8 cells would be filled by player 2 using, say, different color, say blue color chalk. So let me fill the color cells randomly. So say suppose player A fills this hexagonal cell with yellow color chalk. Then player B goes for this cell. Then say this. Then okay. Now he goes for, suppose, this. He goes for this. He goes for this. So I started with yellow, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So it has to be a blue turn, right? Turn off the player 2. So let's say this. Then let's say this. Chalk got broken. Anyway, so you can see 1, 2, 3, 4, 5, 6, 7. Hmm. Okay. Okay. So 8 cells are filled with yellow color. 1, 2, 3, 4, 5, 6, 7, 8. And other 8 cells are filled with blue color chalk. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Fair enough. Now suppose Y is a set of those cells which have been filled by player 1 using yellow color chalk. Okay. And say B is a set of those cells which have been filled by player 2 using blue color chalk. Okay. Now let me further divide Y cells. Say Y plus. Say Y plus are those cells which are able to be connected from left to the left going right. I'm not saying all the way to the right end of the board. No. What I'm saying is B plus would be those cells among all the Y cells. Y plus will be, I'm saying Y plus will be those cells out of all the Y cells which would be able to be connected from left going right. I'm not saying all the way to the right end of the board. And Y minus would be all those cells which are not part of the Y plus. Similarly, B plus would be those cells which we are able to connect from bottom going upward. I'm not saying all the way to the top end of the board. And by B minus would be those cells which are not part of B plus. So now we can we can tell whether this cell is Y plus or Y minus or B plus or B minus. So suppose this. So player 1 will be starting from the left side, right? And this is already Y cell. So it has to be Y plus, right? So this is Y plus. Okay? This is Y plus. This is Y plus. This is Y plus. This can be connected from left to left going rightward, right? So this is also Y plus. This is also Y plus. This cell cannot be connected either to this cell or like this cell cannot be connected from left to the right continuously, right? So this will be Y minus. Correct me if I am wrong. This will be Y minus. This will be Y minus. This will be B plus. This will be B plus. Right? This will be B plus. 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 Whereas this will be B minus. So only one cell is B minus. Okay? Cool. Now, okay, so we have information about Y plus, Y minus, B plus, and B minus. Okay? Let me define a function. So a function is f of x equals to x plus EH. I'm going to define what is EH. If x belongs to y plus, f of x is equal to x minus EH if x belongs to y minus f of x is equal to x plus EV if x belongs to b plus, and f of x is equal to x minus EV if x belongs to b minus. Now this is the function. Now what is EH? See, so basically I told you when I begin this video, I told you that I'm going to treat single point, say central point of each hexagonal cell as whole hexagonal cell only. Okay, so this point will be x only, right? So basically mapping is to be applied on each hexagonal cell, and for our convenience I told you that I'll be treating the central point of each hexagonal cell as that hexagonal cell itself. Okay, so if this is the point, I'm basically referring to this whole hexagonal cell. If I'm talking about say this point, then I'm referring to this hexagonal cell. If I'm talking about this point, then I'm basically talking about this hexagonal cell. So EH is your horizontal vector and EV is your vertical vector. So what I'm telling you, so suppose if this point is to be transformed into some another point, if this point is to be transformed, it is equivalent to say that this whole hexagonal is going to be mapped to some other hexagonal cell. So since this point is going to be transformed to this point, so basically I'm telling you that this hexagonal cell is going to be transformed to this hexagonal cell. And what is the transformation, or in other words, what is the function? That if x belongs to y plus, so suppose this point belongs to y plus because this hexagonal cell is y plus. Okay, if this point is y plus, then x is going to, so EH is your horizontal vector, EV is your vertical vector. So this point is going to go right. Now this is b minus, right? And if x belongs to b minus, then it is going to come down. It will have a vertical vector, and that too also x minus EV. So basically this hexagonal will be mapped to this hexagonal cell. The movement will be vertical and downward. Here the movement was horizontal and rightward. Now in this case, you see, we are going to witness this hexagonal to be transformed to this hexagonal cell because the movement is going to be from this point to this point. Why? Because x belongs to y minus, and the transformation will be, or basically fx will be x minus EH. So this point minus this thing. So basically what I'm telling you is that either we will have horizontal movement, either this side or this side, depending on what exactly x belongs to. If x belongs to y plus, we will have rightward horizontal movement. If x belongs to y minus, then we will have leftward horizontal movement. If x belongs to b plus, then we will have northeastward direction movement. Okay, we will have vertical movement upward, and that too northeast in the northeast direction. If x belongs to b minus, then we will have vertical downward movement. So basically it will be southwest. It will be in south. It will move towards southwest direction. Okay, so far so good. Now I want to tell you. So now, but you tell me, is it possible that this function is not defined in some case? Now you will find that, so since I have filled these cells randomly, now you see this is B plus. Okay, this cell is B plus. Now this B plus, since x belongs to B plus, then we are going to see this cell transform into some other cell, but that is not defined. It cannot go beyond, right? It cannot go beyond. But what we have defined, we have started saying that the function is well defined. Okay, see, to use fixed point theorem, we must have a well-defined function, and we assume that this function is well-defined. But this function will not be defined if we are able to go in this direction. To have this function, which should be well-defined, neither of these four cells should be categorized as B plus, nor either of these four cells should be categorized as Y plus. Because if that would happen, then function will not be defined, because you cannot go further in the northeast direction, or you cannot go further to the eastern direction, right? So if this function is well defined, we cannot imagine continuous path from either bottom to the top or from left to the right. Okay, so if this function is well defined, then this we cannot imagine a board which would result which would have at least which would have one winner always. We cannot imagine that board if we are using this function, because if this function is well defined, if this function is well defined, and then in that case we cannot imagine that one end would be connected to the other end, extreme end, continuously following some continuous path. That will not be possible. If that will be possible, then this function will not be defined. Okay, now so let me tell you one thing. So suppose, so you can see we have bunch of triangles here, right? We have bunch of triangles here. This is also a triangle. All these are triangles only. So suppose this is a vertex, this is B vertex, and this is C vertex. Now it is not hard to assume that, say, let me erase this thing. Say, so if I am going to attach some weightage to each of the vertices, then in that case, suppose lambda 1 is the weightage which is going to be applied to A vertex, lambda 2 is the weightage which is applied to vertex B, and lambda 3 is the weightage which is going to be applied to the vertex C. Now this lambda 1 A plus lambda 2 B plus lambda 3 C, suppose it gives me some vertex, say P. Now what I am telling you is that if lambda 1 plus lambda 2 plus lambda 3 equal to 1, if the sum of lambda 1, lambda 2, lambda 3 is equal to 1, in that case that P will not lie outside this triangle, it will lie somewhere inside the triangle or on the sides, either of the sides, right? So suppose it lies in the center. That depends where it exactly lies. It depends on what are the exact values of each lambda, and what are the different vertices, right? So suppose P lies somewhere inside the triangle. So suppose it lies in the center, right? Now, so now since we are going to map one hexagonal cell to another cell, in a way I'm telling you that we are going to map one point to the other point, right? Okay, now you see this point will either go this side or this side. This point will either go this side or this side or this side or this side. It cannot go in this side, because that's how we defined our function, right? Similarly, this point will either go in this direction. It will be transformed either to this cell or this point, or this point is going to transform to this point, or to this point, or to this point. It cannot go in this direction, right? Neither it can go in this direction. Okay, neither it can go. Okay, that's fine, right? So the movement will be either this or this or this or this. Okay, cool. This is how we have defined our function. Now it is not hard to assume. Now you see, let me think. So this point and this point. Okay, so if we are going to impose the transformation, so if I'm going to impose transformation, suppose on those three, suppose let's consider one triangle at a time. So suppose this, I'm going to transform each of these 3 points into something else, right? Now, so I just told you that, you know, P point, if lambda 1 plus lambda 2 plus lambda 3 is equal to 1, then that point P will lie inside this triangle, right? And if I am going to transform each of these 3 points, so that point P will also be transformed. Now, suppose I divide that function on P as well, then f of P will be equal to lambda 1 f of A plus lambda 2 f of B plus lambda 3 f of C. Correct? Right? So that P point, if that, so suppose, so there will be different P's of each triangle. So those P's will also be transformed, and it is easy to imagine that that P point will always lie inside this rhombus, right? Because I told you that function is well defined, right? And if the function is well defined, it cannot go this side or that side. So that P point will lie inside this rhombus only. And now we meet all the basic conditions of fixed point theorem. The function is, it's not hard to believe that the function is continuous. Function is mapping to itself. Basically, its domain and codomain is same. And now we can impose fixed point theorem that at least one P will exist where Fp will be equal to P. Okay, so there will exist one P, there will exist one point inside this rhombus which will be mapped exactly to itself. So Fp will be equal to P for that particular P point, and there will exist at least one that there will exist at least one such P point. Okay, now you tell me, if point, so suppose this is the point, so suppose this is that point P fixed, this is somewhere here lies one particular point P which is a fixed point, then this point will be fixed only if sum of the vector movement is 0. This is the fixed point. If this is somewhere there lies the fixed point P, and suppose lambda 3 is equal to 0, which should have been applied to this vertex, then this point will stay fixed only if, you know, this point's vector movement is counterbalanced by this point's vector movement. So suppose if this point is transformed to this point, which is nothing but leftward horizontal movement, then that must be counterbalanced by something like rightward horizontal movement of this point. So in a way, I am telling you that this point is to have this point. So basically, if this point is going to be transformed to this point, then this point must be transformed in this direction if we are to witness this point as a fixed, considering that lambda 3 was equal to 0. It's just an assumption. So basically, to have a point fixed, what I am telling you is that we should witness sum of the vectors movement as 0. We should consider the sum of all the vector movements as 0. So suppose if we assume that lambda 3 is equal to 0, then this hexagonal cell must belong to y minus, and this hexagonal cell must belong to y plus. But two adjacent cells cannot belong to both y plus and y minus, or b plus and b minus, and this is the contradiction. So since we started saying that the function is mapped to itself, we are going to use the values of x, and those values are going to be transformed to the same set. So that meets the first condition. The function is defined to itself. The function is going to be mapped to itself. That's first thing. Second, is not difficult to assume that each hexagon is linked to each other. So this function is also going to be continuous. That's second thing. So third thing, which we have assumed, that now the function is well defined. Now if the function is well defined, function is mapped to itself, and function is continuous, then there must exist one point where f of x is equal to x, or f of p is equal to p in this case. But it is mapped to itself, it is continuous, and we assume that this function is well defined, then we should have witnessed at least one point which is a fixed point. But that is not the case. That cannot be the case. So therefore something is wrong in defining the function. And since the function was not well defined, it proves that one will always win this match. One will always win this match because this function is going to be well defined only if neither we are able to connect from bottom to the top, nor we are able to connect from left to the right continuously, following a continuous path. So function is going to be well defined only if neither we are able to connect bottom cell to the top, either of the top cell following a continuous path, nor we are able to connect leftmost cell to the rightmost cell following a continuous path. So since function is not well defined, because we are not witnessing any fixed point, because we don't have a fixed point, it shows that function is not well defined. So we cannot imagine a board. See, if I am telling you that function is not well defined, it is equivalent to say that we cannot imagine a board where neither we are able to connect from bottom to the top, nor we are able to connect from left to the right following a continuous path. So basically, fixed point theorem in this way proves that in such kind of board game, one will always win the match. So that was it. If you have any questions, please drop your comment. I would love to engage in such discussion. And thank you so much for your precious time.